All right, good morning, everybody. What I'd like to do today is kind of give you an overview of research that I've done with many collaborators over the last 10 years or so, maybe less actually, and look at quantum annealing from a very practical point of view. As you know, I work at Amazon, and Amazon is trying to solve real-world problems. And so what I want to do is, I want to start first telling you a little bit about what Amazon does. Don't worry, it's just one slide, where my team fits in and what our philosophy is. And then from that, I'll go to quantum annealing. So Amazon has quantum computing efforts. There are basically three large teams. One of them is Amazon Braket. If you ever want to play with a quantum device in the cloud, you can apply for research credits, and it houses currently 4 different machines. Then you have the Center for Quantum Computing on the right-hand side, which is where we're building our quantum hardware, but also networking devices. And then finally, in the center is the team that I lead, the Quantum Solutions or Advanced Solutions Lab, which is what it's called now, where we work directly with customers to solve really hard problems for them. Now, Amazon has a very interesting philosophy that they call working backwards from the problem or the customer. And what this means is that you usually start with the problem and not with the tool. So if somebody comes to you and says, hey, I don't know how to solve this vehicle routing problem, then you're not going to say, well, maybe you should use this device. You see, we start with the problem, and there, at least in my team, we look at it through the quantum lens, see if this is something that we can tackle on a quantum device. If the answer is yes, great, we can publish a nice POC, proof of concept, show how it would eventually be solved on a large-scale quantum device. And if not, we can augment with, for example, machine learning, high-performance computing, operations research, or combinations of thereof. And so our mission is very simple: prepare customers for a quantum future, but at the same time, because they're paying customers, they want something tangible, deliver a solution that can run in production today. And given the maturity of quantum devices, I think I don't need to tell this to you, anything done on a quantum machine today that has to run in production is going to be relatively limited for very, very few applications, and likely will not be able to apply to many, many problems out there, especially the really complicated ones that you see in industry. So when we look at quantum computing in general, taking a step back from quantum annealing, what are most promising application areas? I think you can divide computational problems very broadly into what I would call big data and big compute problems. We have big data, in principle possible, but as you all know, Grover search only has a quadratic speedup. And when you look at the overhead that you have for loading classical data into quantum memory, pretty much any speedups are gone. So unlikely to be of value. What about big compute problems? There, the typical applications you hear of are chemistry, crypto. I'm not sure, maybe if you lose your Bitcoin wallet, then might be useful application. And then finally, of course, optimization across industry. And chemistry and material sciences, from our perspective, what we've seen working with customers is going to be the more near-term application of quantum devices. Crypto is beyond noisy devices that we have currently today. And as for optimization, as I will show you, only for selected use cases. In principle, you can use quantum devices to solve any kind of optimization problem. In practice, however, this might turn out to be very difficult or impractical. And that's the part that I want to discuss with you today. So what are the challenges that we have when we want to overcome physics-based, or in this case, quantum annealing-based optimization? And this is a little bit how I go now through some of the work that I've done together, first as a university professor, then at Microsoft, now at Amazon. If you have an optimization problem, a real-world problem, then this is, roughly speaking, kind of the flow of how you would tackle the problem. You start with a real-world problem. In this case, let's pick portfolio optimization in finance, which is something that is very close to a quadratic unconstrained binary optimization problem, or QUBO. with some constraints, of course. And the first thing you do is you have to find a mathematical model for the problem. Now, what you see up there, I think we all know what a cubo is basically a quadratic form with binary variables. And this is the magic step, in some sense, that really plays an important role when you're trying to solve a real-world problem. You know, how do you represent the problem mathematically such that a quantum device or any other device can tackle it? Once you've done your mathematical modeling, you can pick your optimizer. It can be any of those, D-Wave, AlphaCube, INQA, Gurobi, whatever tool you want. You run the problem and you obtain a solution. So this is typically what happens. We start with the problem and then we go through these motions. Now let's see what happens if you do this for a real world problem. And this is work that I did with colleagues at NASA and my team several years back. It's about circuit fault diagnosis, a problem that was of interest for the US government at the time. Basically, you have some sort of electronic circuit. You have inputs, you have outputs. There is somewhere an error in there, and you want to figure out where the error is. Now, why is this important? Suppose you're building an aircraft. You have many electronic components. Then you want to make sure that there's no errors in these components. So you want to test all possible combinations of inputs to see what outputs you get. And as you might imagine, this is a nasty combinatorial problem that just blows up. So it's not easy at all. Now, what if you wanted to solve this now on a cubo solver? And I say cubo solver very broadly speaking, because it can be an algorithm, it can be a quantum annealer, it can be a neutral atom device like from QEra. Well, the first thing you do is you write down your math. You have your inputs, I1, I2, C1, you have outputs, CO and the sum. And then you basically have the Boolean equations that represent what the circuit is doing. And this is, in this case, what the circuits that I showed you in the previous slide is doing. Once you have that, you need to convert it into something that is kind of reminiscent of a binary problem that, in this case, a quantum device would understand. And when you do this, you get this thing here. So this is a graph. The little circles represent variables. A triangle means a three-way interaction between three variables. A square means a four-way, so like Si, Sj, Sk, Sl. And this is now the optimization problem you have to solve. You have certain weights on these lines that are the couplers. You have the variables, and you have to find an assignment to the variables that minimizes the cost function. Now, in physics, a lot of things tend to be quadratic. And so this thing now needs to somehow be converted into a cubo. And when you look at the number of variables now, you see right away that they have grown. Now you have only lines between the circles, so two-way interactions. But you incur an overhead because you had to map the higher order polynomial to a quadratic polynomial. Now, once you have this, many quantum devices have a sparse topology. And all-to-all topology is very hard to achieve in physical layouts, especially in superconducting planar type graphs. And despite D-Wave doing absolutely incredible advances and having the most impressive fab, the chip still is quasi-planar. And so at the end of the day, if over here you were to have, for example, a 27 local term, then it would really first blow up in your face to become quadratic, but then you would have to somehow embed this on a quasi-planar graph. This is old results, D-Wave 2. This is basically a piece of history, probably by now. And as you can see now, we went from 3 inputs to outputs and these equations to a problem that has many, many variables. And this is the big challenge that you face when you're trying to really look at a real world optimization problem. If it's not natively a cubo, you're going to have to go through these exercises, and that can be very costly. So as I said, each step incurs an overhead, and this carries over to other applications. Not all of them, but many. And I'll show you later a couple of applications that are natively cubo, or actually one. So what about quantum optimizers today and tomorrow? What about digital quantum hardware? It's unlikely with the noisy hardware that we have today. First of all, it's noisy. Second, the other challenge that you have is that you have small numbers of qubits today. And finally, certain modalities, for example, like ions, have very slow clock speeds. So that if you want to do something variational, for example, like QAOA, it's going to take forever. You know, if you have to do 10 to the 6 shots or runs and it takes milliseconds, well, you can do the math. What about analog quantum hardware? And I'm talking here now very generically. This carries over also for neutral atom systems, by the way, okay, because they are quasi-planar graphs on a Union Jack lattice. So as I said before, first you have to, first you have to embed things, you know, that's bad. You have a mapping overhead, which is what I discussed. And as I will show you, on analog devices, you have analog errors. And then in certain algorithms or algorithmic modalities, you can have a sampling bias, which is a problem when you are trying to solve problems where you have a degenerate ground state and you're interested in finding most of the solutions. So let's talk about embedding overhead. And this is work that I did with Matthias Troyer and Mario Kanz a few years back, 2001, no, sorry, 2021, getting old. 2001, what was I doing then? Oh, PhD. And so the example I want to show you is max cut. Okay, it's a simple combinatorial problem, but it's a nice simple toy problem. You basically have a graph, which is what you can see right here. And the goal is to find a line, a cut, that cuts the largest amount of edges on this graph and splits the graph into 2 subsets. So for example, something like this. And what we did is we generated random graphs, for example, with a density of 30%. We simulated quantum annealing via Monte Carlo in this particular case. And we did different embedding schemes. So we used minor embedding. We used minor embedding on a chimera lattice, for example, also on a square lattice. And then we used this Lechner-Hauke-Zoller approach, where you basically use this parity type approach of embedding problems. And what you can see here is the time to solution of the embedded problem as a time to solution of what we call the physical problem. So if you were to run simulated quantum annealing directly on the original problem, that's this axis. And if you do this on the embedded problem, it's that axis. And what you can see right away that for this particular problem, the time to solution of the embedded problem scales exponentially with the time to solution of the physical problem. And that's a big problem. Because what this means is that by embedding a particular problem into a particular topology, you're incurring a massive overhead. We need to figure a way how to solve this. And the easiest way is focus either on problems that are natively on the topology of the system or come up with better embedding schemes. And so first message of this talk is we need to think very heavily about how to effectively embed problems so that we can tackle them with quantum annealing devices or algorithms. Now, what about mapping overhead? And here we did a very simple example with colleagues from 1QBit a couple of years back, where we looked at relatively simple higher order polynomials. But let's talk about the extreme case. For example, if you have a 27 local Hamiltonian, and there are problems, for example, if you want to look at optimization of traffic lights, where the locality of the Hamiltonian grows with the number of variables. So if you want to look at 50 traffic lights, you will need a 50 local term, so 50 spin variables multiplied together. And so if this number is very high, then there is no easy binary representation, then don't use a cubosolver, okay? But if you look at some higher order polynomial, and interestingly enough, having already third and fourth order interactions in these devices reduces this overhead massively for applications. Now, I know that it's very challenging building these things experimentally, but experimentalists in the audience, I want to encourage you to think about 3-way and 4-way couplers. That would make things a lot easier for embedding. So what we did is we just looked at a simple case. This is without any annealing. This was just pure theory, where we looked at third and fourth order polynomials, and we converted them to a quadratic form. And I think we all know how to do this. X1, x2, x3 basically becomes a product of terms with some additional variables. We did experiments for third and fourth order polynomials. and converted them to second-order polynomials, just random spin glasses. And we looked at the fraction of problems solved. We didn't even bother with time to solution because it was so hard. And what I can tell you is the following. If you ran, in this case, a classical optimizer, we just use parallel tempering Monte Carlo, on the third and fourth order polynomial problems, then we were all able to solve them within the timeout that we had set. But when we looked at the QUBOs, you see that only for the smallest problems, 16, 64, were we able to find the solutions. But then the larger the number of variables was, the harder it was to actually solve these problems. So what happens is that when you convert now a higher order polynomial to a quadratic form, you're actually making your problems harder. And there's another issue that I'm not discussing here in detail, but I want to mention that when you are taking, say, a third order term and then multiplying it out with, as you saw in the previous slide on this equation, with additional ancillary variables, you're also multiplying the coupler values, the different JIJs between the different terms. And what this means is that the distribution of your couplers can broaden because you're multiplying numbers. And then the dynamic range becomes bigger, which again makes your life harder. So if it's close to QUBO, by all means. If not, maybe stay away. What about analog errors? And this is something where there's been a lot of work done since we did this many, many years back with a grad student. Analog errors have gone down considerably. And so it's going to be less and less of a problem. But it's definitely something that one has to keep in mind. Simply because if there are analog errors, you might be solving the problem correctly, but you're not solving the problem that you wanted to solve. Okay? And so what we did here is a very simple numerical experiment. We took a two-dimensional spin glass, random bonds, and then plus minus one. And then what we did is we added some Gaussian noise to the bonds. So you can see there are the JIJs into a JIJ plus a delta JIJ, just some small Gaussian noise of particular width. And then we defined a quantity we call resilience, which was basically if you run the optimizer 10 times, in this particular example, on a classical solver, you count the number of times that you actually found the correct solution, and you look just at the fraction between the number of times that you actually solved the problem that you intended to solve versus the times that you found a solution to a different problem. And then we averaged that over disorder. And so this gives you kind of an idea of how strong the noise influences the results. In other words, are you solving the problem you intended to solve? And you can see some data here. We did this I wrote d by 2x, but it actually is nothing else than a numerical simulation on a camera lattice. And you can see very nicely that when there's no noise, delta J equals 0, well, then you typically are solving the problem you intended to solve. But as you increase the noise, you see that the problems you're solving are not necessarily the ones that you were trying to originally solve. And of course, the more variables you have, the more pronounced the effect is. And so this is something to keep in mind, and this is why it's very important to have error correction post-processing techniques for quantum devices. So second message, think about post-processing techniques. What about sampling bias? This was a big surprise, and it started by me asking Professor Nishimori a cheeky question in a presentation many years back, actually here in Japan. And the question was, if you have a degenerate problem, so some Ising model that has, say, 100 solutions, and you run your optimizer 100,000 times, will you on average find each solution about 1,000 times modulo some errors? And that's an important question for certain applications where you want to have a broad selection of solutions, for example, probabilistic membership filters, where the solution is more important than, the solution string is more important than the ground state energy. And so this is, again, great work that Mario Kunz did. He started playing with tiny little Hamiltonians, up to 5 variables or 6 variables, depending. And when you have this, he actually enumerated every possible graph that you can have. And you see that red and Blue represents plus minus 1. The thickness here represents the strength. But the bottom line is that he exhaustively enumerated every single graph that you can do. Okay? So you might imagine this is quite exhaustive. Once he did this, he numerically integrated the Schrödinger equation for each of these little graphs. And then looked at what you obtain in the long time limit. So let's focus first only on this column here, where we're doing quantum annealing with a simple transverse field. And when you look at the top left panel, you can see that for that particular graph, you have 5 states that you get with the same probability, and 1 state, the dashed blue one, that eventually gets suppressed in the limit of long anneal times. If you look at the middle graph and the bottom graph, you see basically a similar behavior again. There seems to be some state that gets found with less probability than all the others. So we said, well, let's assume we can build a quantum annealer with XX drivers. Maybe that additional mixing might help. And you see that here on the top right, using an XX driver, you find all states now with the same probability in the long anneal time limit. However, for the bottom two, you can see right away that this is not the case. Even doing XX drivers did not help. And empirically, what we found is that if you have a Hamiltonian with 5 variables, then to make really, really sure that you find all states with the same probability, you would need a 5x driver Hamiltonian. So basically, if you have n variables, you need a sigma x to the n type driving Hamiltonian, and that's not particularly practical. I admit this is a bit of a niche type problem in that only few applications out there like that really matter in industry require a broad selection of the solutions, but it is a problem. We also looked at this on the D-Wave device. These were beautiful experiments done by Salvatore Mandra. And you see here a very specific coupler distribution where we did a lot of painful work with classical optimizers to find all ground state strings ahead of time. And what you're looking at here is, this is the disorder distribution. The number of ground states for this set of problems scales like 3 times 2 to the k, where k is an integer. So k is 2, 3, 4, 5, 6. So you have more and more ground states every time. And then what you do is you run the quantum annealer, say, I don't know, make up a number 1,000,000 times, and you count how many times you find each solution string, and then you just rank order them so that you can have some sort of continuous line. And you see right away, for example, for n equals 968, that you find certain strings with high probability, but then about two-thirds of them you don't find at all. Meaning that you're always going into the same corner of phase space. Again, this strongly indicates that post-processing techniques are very much necessary if you're interested in finding all possible solutions. And this seems to be some sort of fundamental issue with quantum annealing. I don't know if anybody has worked on this recently, but we couldn't figure out how to make this work in a way beyond having XXXXXXX drivers, which is not very practical. So what is a partial solution? The partial solution is to try to avoid some of the issues that are hard to otherwise not avoid. And that is use what I like to call nature-inspired, some people call quantum-inspired, which is often not the case because classical simulated annealing has absolutely nothing quantum, but that was Microsoft marketing way back when. And so then we have these 4 issues that are listed here. And if you have an algorithmic approach to annealing or quantum annealing, or if you can build a perfect quantum annealer, then you can get rid of certain issues like embedding, if you have an all-to-all connectivity, analog errors, if you build a digital device, the sampling bias, well, you might use a different type of algorithm than quantum annealing to solve this, but the only thing that remains, and that is always hard to overcome, going back to the beginning of this presentation where I said about real-world problem, is mapping. You start with a real-world problem, you have to convert it into something that a quantum machine understands. And while many of these issues can be worked out either algorithmically or by building better devices, it's going to be very hard to overcome the mapping overhead. Now, what is nature-inspired optimization? I'm not going to bore you with this. Some of you probably all have seen this 100,000 times. The idea is to basically mimic processes in nature. It doesn't have to be quantum. It also can be thermal, like simulated annealing. And so in here, in the case of quantum annealing, where you would anneal with a transverse field, thermally, you would probably have to climb over the barrier. Quantum annealing wise, you would tunnel through the thin barrier. And simulated quantum annealing might give you some sort of better performance, but probably not as good as a quantum annealer as we saw in the previous presentation. You can very nicely see that the quantum annealer has coherence, can find the solutions better, has smaller residual energies, hence me ordering these 3 lines like that. So the idea that we had, and this is a while back, is overcome these QPU limitations by treating physics algorithms as optimizers. And there's other modalities. For example, there is coherent Ising machines. There is the Toshiba simulated bifurcation machine, the SBM, where you can basically use other types of optimization tools to actually look at QUBOs more effectively. Now, let's go back to Amazon. And I think everybody really likes the fact that when you order a package, it arrives here instantly. And I can tell you, the logistics that goes into this is mind-boggling, okay? It's amazing. So you probably don't know this, but when you are on the Amazon website and you're looking for a pair of shoes, then you search for brown shoes, man. You get your list. Then you start scrolling. You pause scrolling. You're like, those look good. Now you keep scrolling. Now you hover over the mouse over this one pair of shoes. You click on it. Nah, you don't like it. You go back. All that data is stored. So the system is tracking your mouse movements, and from there, assigning, using machine learning models, probabilities as to what is the chance that you might end up ordering a particular pair of shoes. Based on that, it will take the pair of shoes from the storage facility and move it automatically to the closest fulfillment center. So that when you come back later and say, yeah, actually, I do want that pair of shoes, it's already in your neighborhood. This is why when you look at something, you change your mind, you come back 2 days later, you click on buy, you have it basically the same day or the next day, okay? Not only that, but I cannot disclose some of the numbers. Let's just say that the volume of orders is enormous. Amazon right now has, I think it is 250 million different products. It's a ridiculously obscene number. And there is a lot of really cool physics that goes, and I say physics on purpose, not just machine learning and optimization, that goes into bringing these products to your doorstep. So, for example, does anybody know how Amazon sorts products in warehouses? Any ideas? Completely randomly. And the reason is very simple. A random walk is going to be always square root of n steps away. And so you have these kind of like vertical shelves where the products are stored, and there's robots that slide under them, lift them up, and can drive them around. And so the number of steps it takes for such a robot to bring the product to somebody that packages it is never going to be more than square root of n. So there's a lot of things like that that are absolutely fascinating if you're a physicist. Anyways, now let's talk about the next step of the process, which is getting it to you. Okay, so usually it goes from a fulfillment center to a, I forgot the name now of that thing. Basically think of it as a staging center. And then, so there's first mile, which is usually airplanes, ships, whatever. Then there's middle mile, where you move the big products to closer to the customers. And then there's last mile, which is the drivers that drive around and drop off the products. And that last mile, I cannot disclose how many, but let's just say that there's about this number of zeros in the number of constraints, okay? So it's a highly constrained problem. And I think we all know if we have a QUBO and we want to bake in a constraint, we have to square it. Now imagine having 100 of those terms. That means you need to optimize 100 penalty terms. if you see where I'm going with this. And it gets really, really, really hard. So simple example, let's take the TSP, 50 stops. You have 50 factorial possible options, no constraint included. If you look at the search space, it's about 10 to the 64. If you take that thing and convert it to a cubo, you're looking at 10 to the 752. So you just made your life considerably harder. Okay? And this is excluding several tens of stops, not just the 50, and several tens of constraints, sometimes even more. And constraints are hilarious at times, like no left turns, for example. Good. So long story short is, if the problem, the real world problem you're trying to solve is not close to a cubo, then don't solve it with a cubo solver. Let me show you an example that is nothing else than a traveling salesperson problem, and this is robot path route optimization. Okay? So I have a little video here. What you're looking at is a car made by BMW, and these are robots spraying PVC sealant around the chassis of the car. And the goal is very simple. The goal is to apply that PVC sealant to the different surfaces in the shortest amount of time with the right amount of material and ideally without bumping into each other. So if I were to tell you, solve this optimization problem, probably you would run for the hills because it's really nasty. You see, you have arms with multiple axes. You can see, I don't know if you noticed, if I do it again, you can see that there's different types of spray nozzles, some that have a thin spray, some that have a broad spray. There is a spray direction. So it is nasty. But the fun thing is that it's nothing else than a sequencing problem. The difference is that instead of having XY coordinates for a vehicle to stop, you have what we call decorated nodes that not only have a coordinate in space, but also a seam index, like which piece of the vehicle you're spraying. You have a direction, go this way or go that way. You have a tool type, there's the order of 3 or 4 tools. Then there's different tool configurations. And then finally, the robots can slide on a linear axis. So this has to be taken into account too. But long story short, if you take all this into account, it's nothing else than solving a TSP. So at that time, we looked at this with a quantum annealer. That's what BMW wanted. And we also looked at it with an algorithm that is called random key optimization paired with simulated annealing. And I'll tell you more about this random key optimizer in a second. RKO is what Amazon uses for middle mile deliveries. So this is what we use to deliver packages to you, okay? And we just took that and applied it to robots. So what about a cubo? Well, first you have to calculate the tour length. Then you have to make sure that only one node is touched per cycle. And then finally, you have to make sure that you only spray every seam once. And this is what that beast looks like. For a typical BMW vehicle, you have typically between 20 and 80 seams, so let's say about 50. When you look at this and calculate it, then the number of qubits is going to be 2 n squared seams times n tools times n configurations times n positions. And these are discretized linear axis positions. And we sat down and did the math. And you can see for a vehicle with about 50 seams, you would need basically 5 times 10 to the 5 qubits. It's not that far away, except that this is before embedding. And then it gets really complicated. Okay? Now, how does random key optimization work? The idea is actually very elegant due to a former Amazon scholar, Mauricio Resende. What you do is you start over here. You know, let's say these are positions in space, decorated nodes, whatever you want to call it. And on the left-hand side, you have a hypercube. On each edge of the hypercube, you have variables that can be between 0 and 1. And then you design a decoder. I put a pot there because this is where the magic happens, that maps between the real world and this hypercube. So let me give you a simple example of a decoder for a sequencing problem like a TSP. Suppose that we run the optimizer on this hypercube, on these chi variables here, and the output is 0.25, 0.19, 0.67, 0.04. Okay, I'll get into more details in a second. The simplest decoder for a sequencing problem is to do an arc sort of these numbers, meaning that you will start with the smallest one, which is the fourth position, 0.04. Then you would go with the second one, which is 0.19, and so on and so forth. And so what this means is when you run an arc sort of that, you get 4213, which basically means you would connect the lines in a particular way. Okay. Now, the cool thing is this is problem dependent. You design a decoder specifically for a particular problem. This part here is completely generic and problem independent. So all you do is you have the system of continuous variables between 0 and 1 in a hypercube, and you run an optimizer on top. In this case, we used a variant of simulated annealing known as dual annealing. What is the advantage? The stuff on the left-hand side stays the same. The brain cycles you need to do are exactly here in this decoder. And there's already many decoder examples that researchers have worked out. So you don't have to do much of the work. ArcSort is, for example, for a TSP type problem. And the cool thing is that for certain cases, for example, here for this traveling salesman problem, every new configuration that the decoder spits out will always be in the feasible space, meaning that you don't have to bake in constraints via penalty terms. Every update is taken care of by itself, and so you will only move within the space that is allowed and never get out of the feasible space. And that's the huge advantage of this method. Here are the results. I know this is going to be very anticlimactic, but you see that the greedy method is what BMW used to use. Red was via QBsolve. You can see it is a bit hard. D-Wave scales surprisingly well, which is very impressive. So if we had a quantum annealer with many more variables, we could do this effectively. And then in blue, you have this random key optimizer with dual annealing. Now you say, well, they scale the same. What's the big deal? The big deal is the difference between the green and the blue line, because that's basically a difference in runtime, and that's around 10%. And it doesn't sound like much, but when you make thousands of vehicles a day, a robot running 10% faster means a lot of more vehicles that you can crank out. So this is now running in production at BMW. Now let me get back to RKO. As I said, it currently powers middle-mile optimization. And I show you here a selection of 4 problems where the decoders will always fulfill the constraints. So one is multi-depot, multi-truck capacitated vehicle routing, job shop scheduling, container loading problems, and then the blood sample collection problem, which is basically a vehicle routing problem with time windows. You want to make sure that whatever biological substance you're transporting gets to its destination in time. So, idea for all of you to ponder about: can we build a quantum optimizer that has continuous variables between 0 and 1, can run on a hypercube? If the answer is yes, then you can use RKO to solve problems that are highly complicated if you map them to a qubit. Now, with this, I'd like to come to an end. We need to think beyond qubits. I think that's a very important step here. I'm not saying quantum annealing is bad. On the contrary, I think it's great. But we need to try to figure out to solve the problems without having to convert them to a qubit. And the reality is that most of the optimization problems out there are not natively qubit. How? We need to think outside the box. We can use qubit solvers as coprocessors that do certain steps in a bigger classical framework paired with machine learning methods, etc. We've done experiments like that too. Or search of high-value qubit native applications. And as a teaser, in the last minute and a half that I have, I want to show you a qubit native application that we recently found. I think everybody has used ChatGPT in one way or the other. And I think everybody knows that large language models are painfully large and take a lot of energy. So we did a project with a customer that I cannot disclose yet. I was hoping the paper would be online by now, but it got delayed, so maybe next week. I think everybody has seen before the structure of one of these machine learning models. You have these layers, that are interconnected. And so the question is, can you take this thing and cut out edges as to reduce the memory footprint of this large language model, and ideally even increase inference times? And so we came up with this idea that is an iterative blockwise optimization method, where you take the large language model, you cut out a chunk, and then basically you optimize this chunk. And the neat thing about this, we use taboo search, okay? The neat thing is that to be able to decide which edges you're going to cut, you basically have to diagonalize a Hessian. And that turns out to be a direct cubo. Okay? So you could, in principle, take a quantum annealer and use it to optimize chunks of large language models such that you can then basically reduce the memory footprint. The outcome, this method that we developed outperforms currently known one-shot pruning methods like Wanda. And as I said, this block pruning can be cast as cubo. So here's some results. On the vertical axis, you have accuracy. So if you were not to prove anything, you would have the black dashed line on top. This is the model Mistral 7B. We also did it for Llama. So 7 billion parameters. So it's a very large cubo kind of thing. And on the horizontal axis, you have the density, how many edges have been pruned. On the right-hand side is no pruning. And you see that methods like Wanda or magnitude, which is what is currently used, of course, decay, but this ICBS or iteratively brain surgeon that we developed decays a little bit slower, meaning that you get more expressivity compared to the other approaches. So the cool thing is, again, this is cubo. And now, because it's Halloween, I'd like to end my talk and wish cubo good luck, hoping that we come up with great ideas on how to use quantum devices that don't require taking a real world problem and converting it into a cubo. And with this, thanks for your attention.
Okay, thank you very much. I couldn't agree more with this final statement. We have time for one question. Yes, over there.
Thank you for a fascinating talk. I'd love to talk much more with you afterwards.
Sure.
So RKO, which is the first time I hear about it, I mean, does it have to be improved? Is it costly in CMOS? Is it costly in software? So why should we do anything to improve it further?
Speed. I mean, if a quantum annealer can basically sample or optimize that hypercube space faster than a classical device, then by all means it should be done. And we have evidence that quantum annealers for specific problems can run faster in wall clock time than classical devices.
Okay, that doesn't sound like it really has to be done from a commercial perspective, though.
No.
It could be done.
It could be done.
Okay.
I'm just giving folks ideas.
Okay,
You know?
thank you.
Maybe time for a very last question. Yeah, over there.
Yeah, I enjoyed your talk. So you gave us one example that's natively cubo, but for this field, quantum annealing to become the next machine learning, don't you think we have to address a wider range of applications, not just
Absolutely.
one here, one there? We can proof of concept, yes.
And so you know, I tried to structure the talk in a way where, you know, I kind of highlight some of the issues we're facing. And as I said, I spent better part of my career looking at quantum annealing and where we should spend our brain cycles to overcome certain problems. You know, I think the technology is phenomenal and it should be applied exactly to where it brings value. But unfortunately today, native cube applications are scarce. And so if you come across one like LLMs that right now is the hot potato in the world, then by all means, you know, might as well do it.
Okay, so let's thank again the speaker and all the speakers of the session. And we have coffee.